Hi folks, welcome back. I hope you're all doing well. Today I want to take a look at an absolutely seminal paper that forms the theoretical underpinnings for shared real-time online editing. We've all used shared online docs where a number of different people may be editing the same doc. They may even be editing it at the same time, and somehow the document is consistent and everyone sees exactly the same document. To support something like that was exactly the goal of the authors here in this paper that was published back in 1989. If you read their list of design goals for this algorithm, it will read exactly like what you want in a modern shared real-time web app. They want response times to be short so that users have a real-time, highly interactive experience. The users are distributed over a wide network. The users can join and leave during the session, and it is very important to be able to resolve conflicts because it is expected that a lot of users will work collaboratively on the same document and in fact on the very same parts of the document. The application that the authors are designing this for is a shared online outline editing system, which of course is very similar to the sorts of docs that we edit collaboratively online today. Now, if you come from a database background, you would think that well-known approaches like locking or transaction processing could be applied to this problem of serializing and making consistent a bunch of edits to a shared data structure. But the problem with that approach is that it really destroys the real-time interactive feel of this collaborative editing. They want to go for this property that they call what you see is what I see, which means that each user must be seeing exactly the same version as all the other users. This is what gives this online real-time session its collaborative feel. You don't want people to wait on locks or transactions getting serialized before they see each other's edits. And this indeed is one of the central innovations of this algorithm, in that the control is completely distributed. There is no centralized locking at all. So let's look at some of the details of the model that they're working with. Each participant in the system is called a site, and the assumption is that sites can communicate with each other over the network. Each site can be uniquely identified with a site identifier, and this shared document that everyone is editing is edited via a set of parameterized operators. If you think about the document use case, these operators could be things like insert the character X at a given position P, or delete the character at a given position P, and so on. At every site, you have a process to send and receive these operations and communicate with other sites and maintain this shared document. A site process can basically do three things. It can generate an operation, so this is when you've locally edited something. And when you do that, the site broadcasts your local operation to all the other sites in the system. It can, of course, also receive operations from other sites. And finally, it can execute operations. Next, we'll define some properties so that we can reason about the correctness and consistency of our shared document. Next, we want to define some properties that will help us reason about the correctness and consistency of our shared document. First, we want to define some notion of precedence. So, given an operation O that comes from a site S and another operation P that comes from a site T, we want to define this notion of O preceding P. Now, if S and T are the same sites, then it's easy because you just say that O precedes P if O happened before the generation of P at the same site. However, if the sites are different, then O precedes P if the execution of O at T, which is the other site, happened before the generation of P at that site. The property that we want to maintain is the precedence property, which states that if an operation O precedes another operation P, then at each site, the execution of O happens before the execution of P. So what this is essentially saying is that every site in the system has a consistent notion of the precedence of operations from every other site in the system. Next, we define a session to be quiescent if all generated operations from all sites have been executed at all sites. That is, there are no edits or deletions waiting to be applied. And we define convergence to mean that when the system is quiescent, all site objects are identical. So note, we don't require all sites to be identical all the time, but we do want them to be identical when all operations across the system have been applied. And finally, the entire system is defined to be correct if and only if both the convergence property and the precedence property are always satisfied. And this intuitively makes a lot of sense because the precedence property guarantees that all conflicts are resolved in a consistent manner. And the convergence property guarantees that everyone sees exactly the same document when all operations have been applied everywhere. Now, one could possibly use one of the various algorithms for imposing a total order on a set of operations generated by a distributed system. But again, the problem with this is that it kills the real-time interactive feeling of the session. You really want something that is lock-free and that can be locally applied at every site without having to coordinate with every other site. But there's a huge problem with doing that, and that is the central challenge that this paper is trying to overcome. And that problem is that simply knowing precedence does not imply convergence. And you can see that from this very simple example. When you have two operations that are overlapping in time, as you have over here, say you start with the string ABCD in your document, and one site generates the operation delete the character at position 3, and the other one generates the operation delete the character at position 2. Since O1 and O2 are overlapping, and precedence is not a total ordering, there is no precedence among O1 and O2. And depending on the order in which you apply them, you'll end up with two totally different strings. So that's something you don't want. And that brings us to the central idea of this paper and the reason that it is titled Operational Transforms, which is that when you are faced with these kinds of situations where you do not know the exact precedence of operations and where the order of execution might give you a different result at different sites, what you do is, instead of executing the operation that you have, you execute transformed operations that are derived from your original operations, such that when these transformed operations are applied to your document, you end up with a consistent, identical state at every site. And when you use this idea of operational transformation, you end up with some very desirable properties. The first one is that local operations are performed immediately. You don't have to wait for some central process to resolve conflicts. So you get immediate local responsiveness on your local copy of the document. The second really desirable property is that there are no locks anywhere. And finally, this is a fully distributed algorithm, and it's resilient to failure in the sense that even if one site fails, all the other sites can still continue their shared editing. At a very high level, the algorithm proceeds as follows. When you do a local edit at a site, that is, when you generate an operation at a site, it is immediately executed locally but then your site generates a priority for that operation. And we will see in a bit more detail what this priority is, and sends it to all the other sites. When you are receiving an operation at a site, there are two cases. The first case is that the sending site has executed operations which have not yet been executed at your site. In that case, you queue up the operation but don't immediately execute it. The other case is the flip side of that, which is that your site has executed operations which have not yet been executed on the sending site. And in that case, what you do is you look at the priority of the operation that you just got, and depending on that, you may have to transform the operation before you execute it locally. So a lot revolves around this notion of assigning a priority to an operation, because that is what helps with tie breaking when there are conflicting edits to a document. Now you could simply use the site ID as a priority, but that doesn't quite work. And the reason it doesn't work is that another third unrelated operations priority could separate those two operations. So what the authors are proposing is to define the priority as not a number, but a list consisting of its largest predecessor's priority plus the site ID. I won't go into the details, but if you're interested in checking this yourself, they have a very simple example in the paper with 3 sites. One generates the character X, another one the character Y, and finally the third one generates the character Z. And you end up in a situation where if you simply use the site ID as priority, one site ends up seeing a different character at the end than another one. Whereas if you use this list notion of priority, you end up in a consistent state. So that was a quick look at the paper that introduced the idea of operational transforms, which underlies shared real-time collaborative editing in shared docs that we all so frequently use today. Since this initial paper, there have been many enhancements and variations on operational transforms, but this paper is what started it all. I hope you enjoyed that, and I will see you next time. Thank you very much.